Hi guys, it's Ms. Hill here, and we are continuing our unit on linear functions, and today we're going to be talking about systems of linear inequalities. So, quick review: to graph just one linear inequality, you want to start by graphing your boundary line, and then we're going to shade either above or below depending on that inequality symbol. In case you forgot from previous math courses, if you have just the plain old less than or greater than sign, that's when you're going to have a dashed line for your boundary line. If y is less than that value, then you're going to shade below the boundary line. If y is greater than, then you're going to shade above that boundary line. If we have y is less than or less than or equal to or greater than or equal to, if you have that or equal to sign on the bottom there, that's when you're going to have a solid boundary line. And again, if it's less than or equal to, then you're going to shade below. If y is greater than or equal to, you're going to shade above. Now, if you're not sure where you're going to shade, anytime you're unsure, use that test point. Okay, and you can pick any point that you want. You just want to check and make sure if it makes the inequality a true statement, then that's where you're going to shade. If it makes the inequality false, then you want to shade on the other side because it is not part of the solution. And a good test point to use is 0, 0 unless it's on the boundary line. And it's just very easy to substitute in 0 for both x and y and simplify. But if it's on the boundary line, then we need to pick another point. But I like picking points that are nice, small, easy to work with when I check. So let's just graph a couple of linear inequalities just to make sure we remember how to graph them before we start graphing systems where we have more than one inequality. So with our first example, we have the inequality 2x minus 4 is greater than y. If it gets confusing having the y on the right-hand side instead of the left-hand side, just flip everything. So we're going to have y is less than 2x minus 4. So now we're in slope-intercept form, and we can see that we have a slope of 2. Y-intercept is at 0, negative 4. So we're going to start by graphing that boundary line just like we would the equation y equals 2x minus 4. So starting at negative 4 on our y-axis, we put our point. And then using our slope of 2, we're going to count up 2 to the right one, up 2 to the right one, get a couple of points there. And now our boundary line, since we have just the plain old less than, we're going to have a dashed line. So that means it's going to look somewhat like this, assuming I can draw a straight line. And then we want to determine if we shade above or below. It's less than, so we're going to assume that we shade below. It doesn't have to be a work of art, just a quick shade. And again, we want to test. My test point that I'm going to use is 0, 0. So there's my x, my y that I'm going to substitute in. And see, does 2 times 0 minus 4 give me something that's greater than my y value of 0? Is that a true statement? Well, 2 times 0 is 0, and 0 minus 4 is negative 4. Negative 4 is not greater than 0. That's a false statement. So 0, 0 is not a solution. So 0, 0 should not be shaded, which it's not. So that means I shaded correctly. All right, let's try one more, and then we'll add on to this. With the inequality 1/3 x plus y is less than or equal to 2, we're not quite in slope-intercept form, not really in standard form either because we have that fraction 1/3. So I'm just going to switch it to slope-intercept form real quick by subtracting that 1/3 x from both sides. So now I'm going to have y is less than or equal to negative 1/3 x plus 2. So I can easily see that I have a slope of negative 1/3. Y-intercept is at 2. Writing that as an ordered pair, that'd be 0, 2. So we're going to start by graphing our y-intercept at that point 0, 2. And then with our slope of negative 1/3, I'm going to count down 1 to the right 3 and down 1 to the right 3. Now this time I have that or equal to, so that means I'm going to have a solid boundary line. So I can draw a nice straight line passing through those points. And I can extend this a little bit further. And then we said y was less than, so we'll be shading below. And we want to check with a test point, make sure that we did shade correctly. Again, using that test point of 0, 0. We can say 1/3 times 0 plus my y value of 0. Do I get a value that's less than or equal to 2? Well, 1/3 times 0 is 0, and 0 plus 0 is 0. And it is true to say that 0 is less than 2. So that means that 0, 0 is a solution. So that part should be shaded, which it is, so I've shaded in the correct direction. Alright, so that's just graphing one simple inequality. Let's take it one step further and look at systems of linear inequalities. So we're going to find our solution just like we did when we were solving systems of equations by graphing, but using that with what we just did on solving or graphing linear inequalities. So we're going to graph each inequality that's in the system, and then our solution, it's not going to be the point of intersection, it's going to be the region where the shading overlaps. So we're looking for that overlap section that we can kind of highlight. So let's look at our first example. If we have y is greater than 2x minus 5, and then we have 3x plus 4y is less than or equal to 12. Let's graph that first inequality, y is greater than 2x minus 5. Easy to graph because it's in slope-intercept form. We start with our y-intercept down at negative 5 on the y-axis. So there's our point, and then we have the slope of 2, counting up 2 to the right 1, up 2 to the right 1. We can get a few points on there, as many as you like. At least 3 is good. And then we have plain old greater than, so that means that we're going to have a dashed line. So drawing our dashed line connecting those points. And then we're going to lightly shade above because we said y is greater than. And then we can kind of check that using that test point 0, 0. Is 0 greater than 2 times 0 minus 5? Well, yes, 0 is greater than negative 5, so that works. We shaded in the right direction. Then for our second inequality, we have 3x plus 4y is less than or equal to 12. We're in standard form here, so I'm going to use my intercepts to graph this one and say that my x-intercept, we can say y is 0, so we have 3x would be equal to 12, so x would be equal to 4, so we're at 4, 0. And then our y-intercept would be let x equal 0, so 4y equals 12, and our y-intercept is at 0, 3. So I can plot those 2 points. There's my 4, 0 and my 0, 3. I have that or equal to symbol in there, so that means that I get a nice solid line through those 2 points. Let's see. Whoops, not quite. Try that again. Something like that. And then we think we might be shading below when we go to put this in slope-intercept form. Again, you can use that test point of 0, 0 to check which way to shade. 3 times 0 plus 4 times 0, that's just going to give me 0. And 0 is less than 12, so that means I'm going to be shading everything below. Now notice I'm shading in a different direction, so it shows up a little bit better. And then the part that is overlapping, so along this solid line from 3x plus 4y is less than or equal to 12, and then along this dashed line here from y is greater than 2x minus 5, everything that's within that doubly shaded part, there is our solution to the system of inequalities. All right, let's try another one. For number 2, we have y is greater than or equal to 3, and then we have y is greater than the absolute value of x plus 2, and then we're going to add 5. It's a little bit different. It's not our typical linear function that we've been working with. And we'll talk about what to do with that inequality in just a minute. But let's start with our y is greater than or equal to 3. So we know this one is going to have a nice solid line that's going to be horizontal because we have y is greater than or equal to just our number 3. So we have a horizontal line passing through 3 on the y-axis. Draw that solid boundary line. And y is greater than, so we're going to shade above. So everything above that horizontal line. Now, we have one of those other equations, and we're not quite sure what to do with that because we haven't talked about absolute value functions yet. So we can make a quick table of values, choose some values for x, plug it into the absolute value of x plus 2, and then add 5, and that's going to give us our y value so that we have ordered pairs x, y. So let's say we choose, let's go with, what do we want to use today? We can use a -3, a -1, 0, and a +1. We'll look at those points and see if that gives us a big picture. Something different is going to happen here. So if we plug in the -3, we're going to have -3 plus 2. Take that absolute value. Well, -3 plus 2 is a -1. Absolute value of -1 is 1. And then when we add 5, that's going to give us 6. So we have the ordered pair -3, 6. Well, look, let's see what happens when we have -1. Well, -1 plus 2, and that's going to give us a +1. Absolute value of 1 is 1, plus 5. That also gives us a 6. Something's going on here. So we have -1, 6 as another ordered pair. Let's try 0. So the absolute value of 0 plus 2, that's going to give us 2. Absolute value of 2 is simply 2, and 2 plus 5 is 7. So our graph is going up the larger we get, at least going from -1 to 0. That gives us 0, 7. And then for when x is a +1, absolute value of 1 plus 2, that gives us 3. Absolute value of 3 is 3. And then 3 plus 5 is going to give us 8. So that means we're up to the ordered pair, oops, not 0, but 1, 8. So it looks like it's continuing to rise there. Well, let's look here in the middle with -2. Absolute value of -2 plus 2, that's going to give us 0, and 0 plus 5 is going to be 5. So it looks like we come down to a point and then it starts to go back up. So we're going to graph those points that we found in our table. And it's going to go off of the grid just a little bit here. But we'll start with -3, 6. We're going to estimate that it would be about there. And if you can hear my cat in the background, I'm sorry. She's a little hyper tonight. And then we have -2, 5. So -2, 5 would be here. and then negative 1, 6. We're back up here, and it's going to continue here. With absolute value functions, it mirrors, so it will reflect and go back this way as well. Now this was plain old greater than. There is no or equal to, so we're going to have a dashed line. So we're going to dash it through here, and it does kind of V at our vertex there. It's going to look something like that. And then it was greater than. So that means that we're going to be shading somewhere in here. And we can choose a point to test and see that everything, if we extend our shading from y is greater than 3, I know we've totally covered up the inequalities there, but if we continue that shading from our first inequality, everything within that absolute value inequality is a solution. So everything in there, that's where it's going to be doubly shaded. All right, so let's look at number 3. This one's a little bit more simple, and I'm going to rewrite this one just because it got covered up by our table. We have x is less than 2, and then we're also going to have y is greater than or equal to negative 1. So x is less than 2, that's our boundary line is going to be x is equal to 2. So that means on our x-axis at 2, we're going to have a vertical line. This one's going to be dashed because I do not have that or equal to underneath my inequality symbol. And x is less than that value, so it's everything that's to the left. Any x value that's less than 2. Then our second equation, we have y is greater than or equal to negative 1. So that means I'm going to have a horizontal line passing through negative 1 on my y-axis. I do have that or equal to sign, so it's going to be a solid boundary line. And this one is greater than, so it's everything shaded above. So the part that is doubly shaded, where it's overlapping from negative 1 on the y-axis all the way over to where we hit that x is 2. Remember, that was a dashed line. And it's everything that is overlapping here. So the green part. So again, those regions where we've shaded and it's overlapping, those are the solutions. You won't be giving 1 point. I might ask you if a specific point is a solution, but I'm not going to ask for a single point. I want to see the graph, see where it overlaps. All right, let's try just a couple more. Now keep in mind, any system is where we have 2 or more equations or inequalities. So we can have 3 inequalities that we graph on the same grid. So if we have x plus y is less than or equal to 12, and then x is greater than 4, and then y is greater than or equal to 2500ths x. We're going to graph all 3 equations on the same grid. The first one, we can use our x and y intercepts if we want to, or we could say that in slope-intercept form, we have y is going to be less than or equal to negative x plus 12. All right, now this one goes off of the grid. So I'm going to change the scale on my axes so that I can actually see everything that's going on. So it's not a very big grid that I have here on my paper. I'm going to change my scale to 3. So I'm going to go by 3. 6, 9, there's the 12 that I need on my y-intercept. And then with the slope of negative 1, 3, 6, 9, 12 here, I'm going to be going down 1 to the right 1, or down 3 over 3. And if I'd used the standard form to find my x-intercept, then it would also be at 12. Now that one was less than or equal to, so I do have a solid boundary line connecting those points. And it was less than, So I'm going to shade below. So everything here. And I think I'll rewrite those numbers in a different color so they don't get overlooked. There's 3, 6, 9, 12, and same thing with our negatives. There we go. Then for our next inequality, we have x is greater than 4. So that means on my x-axis, I'm going to be passing through 4. It's about there. It's plain old greater than, so I'm going to have a dashed line passing through 4. And it's greater than, so I'm going to shade to the right. So everything there. And then the last inequality, we're going to have y is greater than or equal to 2500ths x. So this one is in slope-intercept form. Remember, if there's nothing there, we have our y-intercept at 0, 0. It's at the origin. And then 2500ths, keep in mind, it's the same thing as 1/4. So I'm going up 1 to the right 4. Whoops, that was 3. Up 1 to the right 4. So up 1 to the right 4, so that's going to put me at 8. Up 1 to the right 4. I'm now at 12. And that one was or equal to. So that means I'm going to have a solid line. Something kind of sort of like that. Let's see if I can make it work. There we go. Close enough. And y is greater than. So that means I'm looking above. So the only place where I have everything overlapping, I'll use orange for this one. Looks like we have a little triangle here that's overlapping. So that would be our region. That is our solution. Now, can we work backwards? If we have the graph, can we come up with the equations and write our system? Well, yeah, that's going to be easy to do. So if we're looking at here is our region that has been shaded, we need to see what equations or inequalities we can write. We can see here that we have a horizontal line. So anytime you have a horizontal line, that means we're going to have y equals some number. Well, assuming that we're using a scale of 1, that means that we have a line that's passing through 3 on the y-axis, and then it's dashed and shaded below. So instead of saying y equals 3, we want to use that to say, well, dashed, I'm not going to have the or equal to. Shaded below means it's going to be less than. So I have y is less than 3 for that inequality. Then we can look at our solid line that we have here. So if we have a solid line and it's shaded above, we know we're going to have something that's greater than or equal to. And from here, I can't see my y-intercept, but I can count the slope and use an ordered pair to figure out what it would be in slope-intercept form. So I can see that I have a point where we're intersecting here at -2, 3. And I can also see that I have a point here that's at -3, 1. So I can see that I have a slope of 2, counting up 2 to the right 1, or you could use those two ordered pairs. But we need to figure out our y-intercept. So I'm going to use the point of -3, 1 as my x1, y1 in point slope form. So remember, point slope form, y minus y1 equals m times x minus x1. So substituting in those values, I'm going to have y minus my y1 value of 1 equals my slope of 2 times x minus my x1 value is negative 3, so that becomes a positive 3. And then just a quick distributive property here, y minus 1 equals 2x plus 6. And then we're going to add the 1 to both sides. So we have y is equal to 2x plus 7 as our boundary line. But since it was solid and shaded above, we're going to change that to greater than or equal to. So our second inequality in the system is y is greater than or equal to 2x plus 7. And from there we have our system of inequalities, and we can work it both ways. We can either solve by graphing, or we can write our system from the graph. Don't forget to finish your homework tonight, and you can check your answers on Blackboard. As always, email any questions or send me a remind message, and I'll see you in class tomorrow. Bye.